Hello, so in this video I'm going to go over Edexcel Year 1 AF level Maths, the 2021 paper, the pure paper, paper 1, October 2021, okay? And I'm doing this in supplement to the videos I've done on the topics, right, that I've covered for AS Pure, so I thought I'd go over this a past paper, go over this paper as further exam practice and further support. And so before we jump into the paper then, I just thought I'd take a minute to go over the formula book and the formulas you need to be aware of for the pure paper, right? So for AS pure, these are the formulas you need to know, okay? So these two, mensuration, to do with like shapes and stuff like that, they don't really come up. And to be honest, when they occasionally do come up, these two formulas, to kind of give you it anyway, but it's in the formula book, so just be aware. But not really useful, to be honest. Binomial series, these formulas. This is the binomial expansion, this first one. Now, that kind of just formalizes expanding a binomial, but really, hopefully at this point, you've done a lot of practice with binomials, how to expand brackets using the binomial expansion. It's quite methodical, right? This formula just states it, but honestly, the formula looks a bit weird. Methodically, you should be able to expand it. So the formula, so you don't really need to pay attention to this formula if you've already practiced enough binomials, how to expand brackets, right? The second formula here is the choose function, right? So n choose r is equal to n factorial over r factorial of n minus r factorial. Now this one's a bit more useful, but again, this doesn't really come up, but it's still something to be aware of. If it, I have gone over questions in the binomial section where we need to find like a missing value of n and r, or n or r. Exam question maybe you may need to utilize this formula, but again, the calculator does it for you, right? N choose r is, you can put that in your calculator. So again, it's kind of a redundant formula. Logs and exponentials, again, these two are kind of redundant. This one in particular, the first one, is called a base change, and it tells me if I got log of base A, I can express it in terms of a different log at base B. But that's not really on the spec actually. None of the topics utilize this. It's probably just here to, I don't know, if someone finds it helpful. It's a bit like out of the spec, but I guess the examiners they'll just provide you the formula for any people who find it useful. But this isn't a formula you need to be aware of, to be honest. This formula here, it's basically a more long-winded way of saying the formula e to the ln x is identical to just x, right? It's the same thing, but with just extra steps, right? Because e to the x ln a, which is what you're given here, e to the x ln a is a to the x, right? If I move the x to the front, then obviously e to the ln a to the x is a to the x. And then if I just let y a to the x, then that's saying e to the ln y is y, which is now the same thing, okay? But again, I wouldn't really rely on this formula. I'd just probably try and learn this particular identity here, okay, which you are expected to know. So again, not the most useful. The only formula that is actually useful, to be honest, is this here, first principles. Even then, once you practice enough questions on this, it should become like in memory, but you are given the formula to differentiate by first principles here, okay? So you don't need to learn that, but maybe if you practice enough, maybe you'll pick it up anyway. But that's all the formulas. Again, honestly, the formula book ain't the most useful, to be honest. But yeah. Okay, so let's go over the paper. Also to note, it's 100 marks, and usually there's about 16 questions, right? And it's 2 hours long. Okay. We got this question firstly. Before I go into it, this little text here you'll see on some questions if you look at past papers. It says solutions relying on calculator technology are not acceptable. That means basically you must show you're working, but more particularly you can't just write down the answer using your calculator alone. Okay, you can't just jump to writing the answer from your calculator, because the calculator has a function like with quadratic equations. It will just solve quadratic inequalities like that if you just put in the inequality. What that's saying is, don't just use the calculator to get the answer. You don't use the solver function to write down your answer, okay? Because you're not showing any work and you won't pick up any marks. Have a look at the actual question now. We're told using algebra. Again, this command word, this key phrase using algebra means show all your working. And that even means showing how you solve a quadratic equation, okay? So you might want to factorize, you might want to just write down the quadratic formula. That's what it needs to show all your working when it says using algebra, okay? So again, don't just use your calculator to skip steps. Okay, so using algebra, solve the inequality x squared minus x is greater than 20, okay, in set notation. Okay, so this is just a standard quadratic inequality. So if we move the 20 to the left, subtract 20 is greater than 0. And so at that point we sketch this quadratic. So firstly we're interested in the critical values, and that is basically the solutions when we solve the equation, right? If we were to set it to 0, then we can solve it. And honestly, in the exam situation, if you just bog down about, oh, should I factorize or whatever, it doesn't matter. But I'll just write, what I like to do is just write down the formula very quickly. So the quadratic formula is 1 plus or minus the root of minus 1 all squared, take away 4 lots of 1 and minus 20 over 2 lots of 1. What I've done here is technically show normal working, right? The quadratic formula. What I can now do, instead of typing this formula in the calculator, I can now kind of just use the quadratic solver function on the calculator. That's fine because I've shown my working at this point, right? I've shown how I get the solution. So if I put that in the calculator, I get the solutions. X is 5, x is minus 4. Those are my two critical values, essentially roots. So at that point then, I've got my roots that allows me to sketch the quadratic. So again, it's a positive quadratic, and the roots are 5, somewhere there, and minus 4. So the quadratic will look something like this. Okay. Now, to solve the inequality then, pay attention, it's greater than 0, which means it has to be above the axis. It has to be above the x-axis. So it's going to be the region above the axis. So these two regions here. Okay, when the graph is on top of the axis. And so actually then, these two regions, firstly this region here is when x is less than minus 4. Or the other solution, the other region, x is greater than 5. Okay. And that's my answer. The final step is to write it in set notation. So, remember with set notation, obviously it's the curly bracket, right? It's this sort of curly bracket. But the key idea with a set, right? We say x dot dot, that means x such that. Then we write down an inequality. But the key idea is you can only have one inequality per set, per bracket, right? So I can't say x greater than 4 or x greater than 5. I can't say that. I have to split it up into two different inequality sets. So x less than minus 4, that's my first inequality. Then I'm going to close it. And then I'm going to introduce my other bracket, my other set, so x such that then x greater than 5. So all I've done is just a fancy way of writing down my inequalities, but Obviously, then you'll say or, so you'd have one inequality or the other one, right? But we can't use words, right, with sets. And so remember, or is this U shape here, okay? I like to remember it because U, like, kind of has like an O sort of shape, vaguely. And N, which means and. So U means or, effectively. N means and. N has like an and, like the N pronunciation. U has like an or, like a U, like that sort of pronunciation. That's how I remember it. But that is set notation, okay, as my answer there. Okay, so we've got this question, and again, you'll notice the same text right at the start. That again means you can't just use your calculator to write down the answer. Okay, you must show your working. So now we're given this equation here. So 9 to the x minus 1 over 3 to the y plus 2 is 81. And we're told to express y in terms of x. So y is some function of x, right? Some expression of x. Right, so hopefully you recognise we are dealing with powers here, power laws. And so the kind of idea with these is kind of recognise, well, actually everything here is in terms of 3, right? Obviously got 3 here, but 9, I know that 9 is 3 squared. I also know that 81 is 3 to the 4, right? Because you've got 3, then 9 times 3 is 27, and then 27 times 3 is 81. So actually, now I've got everything in terms of 3, right? So now I can say that, well, 9 to the x minus 1, if I say 9 is 3 squared, then I can say 3 squared, all then raised to x minus 1, divided by 3 to the y plus 2, is equal to 81, which is 3 to the 4. Now it's a lot more clearer how we can proceed. I can notice I can sort of expand this bracket. So remember the power law, a to the m, all raised by a different power n, are times the powers. So what I'm going to do here to sort of expand it, I'm going to times the powers. So that'd be 3 to the 2 times x minus 1 over 3 to the y plus 2 is 3 to the 4. And so if I expand this then, right, that'd be 3 to the 2x minus 2. So what we can do here, the two things you can do here at this point, obviously you could recognise we are dealing with a division. So remember when we're dividing, right, if we're dividing different powers, we subtract the powers. You could do that. But I guess probably the most, I guess, sort of straightforward approach maybe is kind of like how you solve a fraction in general. We could just multiply by 3 to the y plus 2. So that'd be 3 to the 4 times 3 to the y plus 2. Okay? It's like how you solve an equation, like you rearrange to get y on its own sort of thing, right? And so at that point, it's becoming a lot more apparent where I'm going to end up. But actually, because I'm multiplying now, I've got this. I can use the power law where a to the m times a to the n, multiplying with different powers, I add the powers. So here I'm going to add the powers. So 3 to the 2x minus 2 is going to be 3 to the 4, add y, add 2. And actually this simplifies to 3 to the 6, add y. And so actually, because at this point the equation's obviously left hand side is the same as the right hand side, it's the same base 3, so that means the powers have to be equal also. So I can deduce that 2x minus 2 is 6 add y, or y add 6, let's say, right? And so if I just simply subtract 6 from both sides, then y is 2x minus 2 minus 6, which is minus 8. And there we are, that is y in terms of x. Cool. Okay, question 3. We need to find the integral of 3x to the 4 minus 4 all over 2x cubed dx in simplest form. So this is a standard integration question. So obviously first we can't just integrate it as it is. We're going to need to use power laws to kind of to simplify things. But first, with fractions, it's best to split up the fraction. So this is equal to 3x to the 4 divided by 2x cubed, then take away 4 over 2x cubed dx, and now I can proceed to use power laws. So that would be the integral of 3 over 2, then that's x to the 4 over x cubed, right? So I factored out the 3 over 2 here, so I get x to the 4 over x cubed. Okay, then I'm going to take away, well, 4 over 2, that's just 2, that's 2. That's 2 over x cubed dx, and so at that point then, recognise now I can use power laws again. So here, this is x to the 4 divided by x cubed, so I subtract the powers. So 3 over 2, if we subtract the powers, x to the 4 minus 3 is just x to the 1. Well, that's just x then, right? There we are. Then we're going to take away 2 over x cubed. So I can say that's 2 over 1 over x cubed. But this is a reciprocal, so I can make that a negative power. So that'd be x to the minus 3. Right? Now at that point, these are all nice powers that I can integrate. Remember that the idea at the end of this, I need to be able to integrate x to the power n. I need to make sure all my x's look like this. Okay? And now it is. All these x's are in this form here. And so then I can proceed to finally integrate. So remember when we integrate, we add 1 to the power. So firstly here, 3 over 2x, that's x to the 1. We add the power, so it'd be 3 over 2 x squared. Then we divide by the power, so all over 2. Okay. Any coefficients, we just leave it where it is. So it's still 3 over 2 in the front. Again, then we have minus 2. And then x to the minus 3, we add 1 to the power. So it'll be minus 2 now, divide by minus 2. Okay. And remember what else? We must have a plus c. Always a plus c, because if we were to differentiate this back, differentiating plus c goes to 0. So we need to account for that. So always a plus c at the end. And lastly, we can just simplify what we've got here. So the first fraction here, 3 over 2 divided by 2. If you say do 3 over 2 divided by 2 on the calculator, you would get 3 over 4. So that's 3/4 x squared. Then we're going to take away, now this is saying minus 2 divided by minus 2. That's just plus 1 then, right? So that's just plus 1. That's just plus 1 x to the minus 2. But of course that's just itself, right? So it's just x to the minus 2. And then we add our c on the end. And that is it. That is my final answer. Okay. Cool. Okay, so now we've got this question, and you'll notice it's slightly picking up now in the difficulty. And so before we look at the question, you got this little text here. Sometimes they just say that it says the unit vectors I and j, so you should know what I and j means. I is basically the x component, the x-axis almost, and j is sort of the y-axis part, right? So I and j are east. Well, I, that's east direction, and j is the north direction. Okay, that's all that means. It's just saying, well, kind of what you already know, right? I is x and j is y, essentially. Anyway, so the question says a stone slides horizontally across ice. Initially, the stone is at the point A, minus 24i minus 10j, relative to a fixed point O. Now, O is the origin. Okay, O is just the origin, just shortened. After 4 seconds, the stone is at the point B, 12i, 5j, relative to origin again. The motion of the stone is modelled as a particle moving in a straight line at constant speed. Using the model, prove that the stone passes through O, the origin. Right, so the main idea here is, well, these points A and B, because they're what we call relative to O, basically means it starts from O. Okay, so if you have to say a point A here relative to O, so we have an origin, just means it's a vector starting from the origin to the point A. And so because of that, you can think of it, it's a position vector. and you can think of it as coordinates, right, in sort of on the XY grid, right, because it's from the origin. Okay, so position vectors are basically coordinates. So these two vectors here, this vector A and vector B, are position vectors. So I'm going to say OA is, as a column, minus 24i and then minus 10 on the bottom, and OB is 12 and 5. Okay, now the other key part is we want to prove that the stone passes through O. So what's happening is the stone it starts at a point A and then it ends at B. So if I were to sort of roughly sketch the idea, the particle starts at A and ends at B, right? And we want to prove that the stone passes through the origin, this point O, the origin, somewhere on the line, let's say here, right? Now we're in a situation where we want to prove that 3 points are on the same straight line. We want to prove that A, O and B are on the same straight line. Now that is actually a standard vector question. That is proving that 3 points on the straight line. We want to prove 3 points A, O, B are on the same line. Okay, that's what we want to prove. That's actually a standard vector problem. Hopefully you would have seen that. And so to do that, if you want to prove that we're on the same line, the standard vector technique is we can make three possible vectors on this line here. We could go from A to O. We could go from O to B. Or we could just, as a whole, go from A to B, right? So we can obtain these 3 different vectors, but the idea is all of them, if they're on the same line, they all have to be in the same direction, obviously because on the same line, same gradient if you will, so they're all parallel. Right, that is how we prove it. But to do that, we only need to pick any 2 of 3 vectors. We don't need to deal with all 3 vectors. We just need to pick 2 of them and prove that they're parallel. So I'm going to take AO and OB, right? So the vector A to O is parallel to O to B. That's what I want to pick. I want to show AO is parallel to OB. And actually that's sufficient, okay? Just prove any 2 of these vectors are parallel. We're great. And then to show that 2 vectors are parallel, then we need to show that they're multiples. So this vector AO is a multiple of OB, okay? That's what it means with 2 vectors to be parallel, if you recall. So we want to find out it's a multiple of K, some multiple K of the other vector. So, right. So firstly, let's find this vector AO. Now, A to O, we can also go the other way and go the negative of OA. Okay, we can flip the vector around by doing the negative. But we know what OA is. It's minus 24 minus 10. So, that is minus of minus 24 minus 10, which is just positive 24, positive 10. Great. And also OB, well, we already have it. OB is 12, 5. And so then we want to show the multiples. So in other words, we want to show that this vector AO 24, 10 is a multiple of K of 12, 5. So we need to find K. So to do that, we just simply, I guess, sort of write down an equation. So the top part 24 has to equal K lots of 12. Okay, 12K. Therefore, we can show that K is then 24 divided by 12, which is 2. Does that work with the bottom number then? So then 10 is going to be 5K, the bottom part. Well, indeed, K would still equal 2. So that is a solution. So then we can say that 2410 is indeed 2 lots of 12, 5. So there we are. We've shown that it's a multiple. We've shown that AO is now 2 lots of OB. So they're parallel. So it's parallel to OB as they are multiples of each other. Okay, and so what that means is overall then, because we've shown that these two vectors on the line are parallel, that means that the points AOB all are on the same straight line. And another thing you need to add is because the other part that makes it work is not only is that the two vectors are parallel, right, on the same line, also the two vectors here have to share a common point. Here, the common point is O, because they share the two vectors, the common point O. And that's it, we're done. And so because we're on the same line, then therefore the stone must pass through O. Right, because well, O is just on the same, is on the line that the stone is on, right? And there we are. So that's the standard vector approach. What you could have done instead is, if we just again take these points, again as I discussed, they're position vectors, we can treat them as coordinates. If we were to imagine plotting these 2 points on a coordinate grid, if I do it down here, so I'm going to say, or the other approach, alternatively, instead of the vector approach here, so minus 24 minus 10 for A, so it would look perhaps down here somewhere. That's A, minus 24 minus 10. And then B is 12.5. So 12.5 would be somewhere there maybe. And so if we connect it, if we connect the line, right, if we connect the 2 points, we get this straight, well, supposed to be a straight line here, and you can see it roughly passes through the origin, but does it exactly does it exactly go through it? How are we going to show that? Well, at this point we just converted this problem into a straight line sort of problem. So what we can do here is, if we want to prove that this again O, this is again the line from A to B is where the stone is where the stone moves from. So we need to show that O is on the line, kind of like what we did just right. We want to show that O is on the same line. To show that, well, let's just work out an equation from A to B, because we've got the 2 points, right? So again, any straight line, y is mx plus c, has a gradient. Well, the gradient, that's going to be changing y, changing x. So at B, y is 5. Take away minus 10 from A. Then changing x is 12. Take away minus 24. If we work that out, we get 5 over 12. That's my gradient. So that means m is that equals m. So m is the gradient is 5 over 12. So that then we can say that y is 5 over 12 x at c. Then to find c, well, I could just substitute a point in. So let's substitute b in to here. So then b is 12.5. So sub 12.5 into this line here. If I do that, y is 5. That's going to be 5/12 of x, which is 12. Add c. And then we get 5 equals 5 at c. Therefore c is 0. Well, actually, we're done here because that's telling me the y-intercept is 0. So it passes through, it has to pass through the origin then, because that's the y-intercept 0 has to be the origin. Alternative, so I'm going to say, therefore, as y-intercept is 0, the stone must pass through origin. Okay, this line here, so the stone which is moved on this line here, 5 over 12 x at c, means it has to pass through the origin. Alternatively, if you didn't realise that, if we then sub c 0 into here, then y would simply simply be 5 over 12x with nothing on. If we then wanted to show the origin is on the line, if we sub the origin, which is 0, 0 in, we would indeed get 0 equals 0 into this equation, which is correct. So it does indeed lie on the line. So the origin lies on the line in that way as well. Okay, so there are many ways we can approach that. Okay, part B. Have to do it down here. Okay, now it says calculate the speed of the stone. The speed of the stone. So, okay, again, if I plot the line A to B, right? A to B. So we have A here and B here. The A is the vector minus 24 minus 10, I think. Yes, and B is 12, 5. So that's the stone's movement from A to B. If you want to calculate the speed, there's two ways you can calculate speed here, right? You can do distance divided by time, the more, I guess, basic formula, or if we're given a vector, a velocity vector, it'd be the magnitude of the velocity vector, but we're not given any velocity here. So actually, we're just going to resort to this formula here. And we know that's going to happen. We know we're going to need to use that formula because it's talking about time here, 4 seconds. So that's my time, right? From A to B, it's 4 seconds. That's given. So time is 4 seconds. So simply, we just need to work out the distance. So the length of the journey, the length of the distance from A to B. Well, actually, we've got the 2 points, right? So we could just work out A to B, the vector A to B, right? And then take the magnitude. That would be the distance, right? So, or alternatively, you could convert these into points and then just do the distance between the 2 points. Either works, okay? But as in terms of vectors, then the vector AB, again, in terms of position vectors is OB, take away OA. So that's 12, 5. Take away minus 24 minus 10. So then we do 12 minus 24, that'd be then 36. 5 minus 10 is 15. So the magnitude of that, the length of AB, is going to be the root of then the 2 parts. So 36 squared add 15 squared. And so that would be just 39. Cool. So that's telling me then that the length, the distance of the line from A to B, where the stone has travelled, that is just 39. Right? So my distance is 39. And that'd be in meters. Again, it's in meters because it references meters here. Okay? So therefore the speed is then simply going to be distance over time, so 39 over 4. And that would then be in meters per second as my units. Make sure you do try and include your units. Sometimes they're quite stingy, quite strict. You might not get the mark if you include the units on. So make sure you do that. But yeah, so that is that question. Okay, here we are given a curve. The curve y is equal to 3x squared minus 2. We're given the point P, which is 210. Is on the curve. Firstly, it's asking me to work out the gradient of the tangent at the point P. So remember, a tangent line, it kind of touches the curve at that point. A very bad curve, but it touches the curve at that particular point. Right? I can't draw, but there we are. So that the tangent is all to deal with the gradient, right? So how do I deal with gradients? The gradient is all to do with the derivative, right? It's dy dx. So I know y is 3x squared minus 2. So then if I differentiate this, that would be, well, again, if we differentiate the power rule, so with differentiation, we bring the power to the front, so it'd be 3 times 2, that's going to be 6x. Then we knock 1 off the power. So 2 take away 1, which is 1, that's just x. And then any constants go to 0, so it's just 6x, right? There we are. And so therefore the gradient at P at P, again, we're given that it's 210, that's x is 2. So when x is 2, then the gradient, the derivative, dy dx is 6x. That's 6 lots of 2, which is 12. And there we are. So that's the gradient, 12. Cool. Then part B says the point Q with x coordinate 2 plus h also lies on the curve. It says to find the gradient of the line P to Q. Right. So P to Q, so again Q is here. Right, so if I add that coordinate on, so it says the x coordinate is 2 plus h, or h plus 2. But we don't know the y coordinate, right? Now, it says the gradient of the line. Well, again, the gradient of a line, so the gradient of PQ, the gradient of any line is just changing y, changing x, right? So again, as I remind you then, we calculate the gradient, the change in y, change in x, of points P and Q. But I was told that P was the point 210, and Q, as I remind you, Q was up here. I said it's h plus 2 for x. And y, I'm not given a y coordinate, I'm only given the x coordinate. How can I work out the y coordinate if I'm given the x coordinate? I can just simply substitute that into the curve, right? So then I'm going to say that y was 3x squared take away 2, I believe. Yes. So then if I sub x is h plus 2 in, that'll be 3 lots of h plus 2 all squared take away 2. Again, don't panic. Obviously, there's a h. There's some algebra here, but it works in the same way. The same sort of process. So if we then sort of expand and simplify this, we get 3 lots of h plus 2 squared. That's going to be h squared. Add 2h, add 2h is 4h. 2 squared is 4. Add 4. Then take away 2 at the end. Then we can expand it to get 3h squared. Add 12h, add 12, take away 2. That is 3h squared, add 12h, add 10. Okay. So therefore my final coordinate for Q, so P is 210, Q is h plus 2, 3h squared, add 12h, add 10. So therefore, the gradient PQ, M of PQ, right, the gradient PQ, changing y, changing x. So y at Q is 3h squared, add 12h, add 10. Take away the y at P, which is 10. Take away 10. Then changing x. That's h plus 2 for y, for Q. Take away 2 for P. And actually then we can simplify, right? We can simplify the top and bottom, because I've got 10 take away 10. That cancels out. So I'm left with 3h squared add 12h over h. Then plus 2 take away 2 cancel, so I'm left with h. And actually note, so I can factorise h on the top. So 3h add 12 over h. And then I can cancel the h out to be left with 3h add 12. And that is my gradient in terms of h simplified. There we are. Cool, then part C says explain briefly the relationship between part B and the answer to part A. So as I remind you, okay, part A, the gradient was 12. So the gradient, the tangent at P was 12. There's no more room here. So remember part A, it was 12. Part B, we have 3h at 12. It says to explain the connection between these two answers. Well, hopefully you recognise what we've done here. It's kind of first principles, right? But in disguise. So remember, the end step with first principles is we let this h go to 0, right? So actually, the relationship is, as h tends to 0, 3h at 12 tends to equals 3 lots of 0 at 12, which is your 12. Well, that's the answer to part A then. So therefore I'm going to say that as h tends to 0, the gradient of PQ tends to the gradient of the tangent at P. So remember, so the gradient of PQ, right? That's what we worked out in part B, and so it tends to the gradient of the tangent, which we worked out in part A. So we're basically saying the part B, the two answers become the same when we set this h to 0. Okay, and yeah, so there we are. Okay, question 6. Again, as I remind you, this here, this text here, we're going to be dealing with quadratics. So that means we can't just pull it in the calculator, and that's further evidence because it says here using algebra, which again remember means show all your working, even showing how to solve a quadratic. Don't just pull it in the solver function. Okay, so we need to find all the solutions to 3x cubed, take away 17x squared, take away 6x equals 0. So the first thing to know is actually like a factor in Excel. X is common. So x of 3x squared, take away 17x, take away 6 equals 0. So that means if I set each factor to 0, again, x is a factor here, right, pretty much. So that means either x is 0 or this quadratic factor equals 0. Well, obviously we know x is 0, cool, but now we need to solve this quadratic. So again, I'm going to show my working. The easiest way to show your working is simply just to write down the formula. It takes no thinking, right? So if I just jot down the formula to show my working out, that'd be 17 plus or minus the root of minus 17 squared, take away 4 lots of 3 lots of minus 6 over 2 lots of 3. And so if I just simply, I'm not going to put the formula, that nasty fraction, in the calculator. Now I'm going to kind of secretly jump to using the quadratic solver function to do it quickly. But I've shown my working. And so the solutions I get is x is 6 or x is minus a third. And so those are my solutions. There. Okay, x is 0, 6 or minus a third. Then it says for part B, hence, again, command word hence means basically you got to use your answer to part A somehow. Find all real solutions to this equation here. To 3 lots of y minus 2 to the 6 minus 17 of 1 minus 2 to the 4 minus 6 of 1 minus 2 squared equals 0. Okay, hopefully you spot here, this is a disguised quadratic. And hopefully you notice that because we've got 3 lots of something, which matches this, 3 lots of something, minus 17 lots of something, minus 6 lots of something equals 0. They're symmetrical, right? These two equations. But obviously the only thing that's different is the variable here. So here I've got x cubed, 1 minus 2 to the 6, x squared, 1 minus 2 to the 4, x 1 minus 2 squared. Well, to solve this then, I can just use a substitution. I notice here that x indeed, right, x will have to equal the y minus 2, all squared, right? That matches then, right? And so actually, in order to solve this equation here, the more complicated one, I can just basically use this sort of substitution, this link between them because I know what the solution to this quadratic is. So essentially, if I state this then, that x is y minus 2 all squared, then actually the solutions to this harder equation I'm given here is simply just going to be the same solutions to x here. But of course, if x is 0, or x is 6, or x is minus a third are my roots for x, then I can solve for y by using this. So then y minus 2 squared is 0. So then y minus 2 is, well, plus or minus root 0, that's just 0. So then y equals 2. That's my first solution for y. Then x is 6 would mean y minus 2 squared is 6. Well, is 6, right, just using the substitution. Then y minus 2 is plus or minus root 6. And so y is 2 plus or minus root 6. Then lastly here, x is minus a third, so y minus 2 squared is minus a third. And then actually, if I was to root it, so plus or minus root of minus a third, that cannot happen. You cannot root a negative. At least for normal maths, we can't root a negative. That leads me to no proper solutions I'm interested in here. So there are no real solutions from here because you can't do a root of a negative. So that leads me simply to the only solutions: y is 2, y is 2 add root 6, or y is 2 minus root 6. And there we are. Okay, so here we have this question here, and we're told a parallelogram PQRS has area 50, and we're given that PQ is length 14, QR is length 7, and angle SPQ is obtuse. We first need to find the angle SPQ. So again, with these sort of questions, it's best to just do a very rough sketch of what it looks like. So PQRS, let's say we have P here, then Q here, then R, then S, let's say, some parallelogram. So the shape will stuff it roughly like this. Okay. And so PQ is length 14, QR is length 7, and we're also given angle SPQ, so that's going to be this angle here. So again, with angles, the middle letter is where the angle's at. I'll call that theta, right? So we're told that, there we are, we need to find the angle SPQ. Right, so probably the best way to deal with this is to split it into two different triangles. Well, actually, firstly, we know because it's a parallelogram that the length 14 here has to be 14 here. Likewise, 7 here. And so actually then, if we split it into two triangles, why triangles is because we can't do anything the way it is, but as a parallelogram. But if you split it into a triangle, I can do all sorts, right? Because anything to deal with angles, I kind of want to split into triangles and use SOHCAHTOA, cosine rule, stuff like that, right? So split into a triangle. Best way to split it through the diagonal. So then you can notice I've got this triangle here, right? P, Q, and then S, and then obviously I want to find that angle here, and I also know this is 14 and that's 7. Doesn't look it, obviously it's very dodgy diagram. It should be the other way around really, but that is the diagram we've got. So I'm in a position where I want to find this angle here, but I've got the two sides next to it, but I don't have the third side. Right? So what can I do here? Okay, but I'm told the area additionally is 50. So actually that means the area is 50 for both triangles, but of course, if I'm splitting it through the diagonal of a parallelogram with in this way. The two triangles here. So if this is triangle 1 and triangle 2, if the total area both is 50, then individually they're 25. Okay, they halve. So that'd be, this triangle would be 25 centimeters squared and 25 centimeters squared. The two areas would be 25 to add the 50. Okay, so additionally, I know the area is 25. So what can I invoke here? I can invoke the formula area is a half AB sine C, right? And so it's a lot more apparent now. I can use this. So now I know the area is 25, and I got the angle and also the two sides next to it, 7 and 14. So this is a half of 14 times 7 times sine of theta. And so then if I work this out, if I simplify, so a half of 14 times 7, that's 49. So 49 sine theta. Therefore, sine theta on its own, divide by 49, 25 over 49. And so then if we do inverse sine of this to get the angle, we will get we get 30.677 degrees. That's my angle, except it isn't, because hang on, it said it's obtuse. Obtuse means it has to be between 90 and 180. We've got 30 degrees. That's acute. How on earth do we get obtuse? You need to remember. You need to remember the ambiguous case. Okay. So when we're dealing with angles, particularly this is to deal with sine. Sine theta always produces two possible solutions in this case. So what we always must be doing when we're solving for sine to get the angle, there'll be another solution. So if we look at the sine graph, so again the sine graph, let's say between 0 and 180, the first 180 degrees of the sine graph. Obviously it would look like that afterwards. But between 0 and 180, if my first solution is, let's say, 30.7, so it'd be somewhere there, then actually the next solution we read across would be somewhere there. So to work out the next solution, well, again, it's symmetrical in the middle of the graph. So that means either end. So the gap between 0 and 30.7, that's 30.7. That's the same gap between the second solution and the other end of the curve at 180. So that would be 30.7. So to work out the next solution here, that'd be 180 take away this 30.7. So the other solution is 180 take away this 30.677. Okay, so it's kind of like just solving a trig equation, right? So if we work that out, 180 take away this answer is 149.32 blah 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 degrees. That is obtuse. That is my solution. Okay, so all to 2 decimal places. There we are. Cool. So that is my solution. Okay, so I'll make a note of that. Say theta is obtuse. So to clarify, this is my only solution. Theta is 149.32 degrees. Okay. So make sure you are aware of this ambiguous case, okay? Make sure you are aware of it, and how you must always consider the other solution when solving for sine, because of the way the graph works here. We get another possible solution in this case. And that is the solution. That's obtuse. Great. Then it says part B to work out the length of the diagonal SQ. So actually now if we look at this triangle we've got here, then if I get rid of the area, we don't need it, but we know the angle now. This angle is 149.32 degrees, right? So actually, how can we work out this? If I call that xn, qs, the diagonal sq, how can I work out x if I'm given two sides and an angle? I can use the cosine rule, right, to then work out sq. So if I use the cosine rule here, so remember the cosine rule is a squared is b squared add c squared, take away 2bc cosine of a. So then here, my missing side is x. X squared is the other two sides, all squared. So it's going to be 14 squared and 7 squared. Take away 2 lots of 14 times 7. Cosine of the angle, which we worked out in part A, 149.32. And so at that point, we just put that in the calculator to say that we get x squared is 413.57046. So therefore x, if we root that, we get 20.336. Of course, you don't do plus or minus here because obviously it will only be positive because it's a length. And to round it to one decimal place, if we were to round that, that would be 20.3. What are the units? Centimeters, right? That was the units, wasn't it? Yes, the unit centimeters. And there we are. Okay, cool. There we are. So again, the cosine rule is handy, particularly when we're in a situation where we're dealing with all three sides and one angle. So that's why the cosine rule was used there. Okay, question A. We got a binomial expansion question. Okay, so we're told that g of x is 2 plus a, some number a, lots of x to the 8. Given that one of the terms in the binomial expansion is 3402 x to the 5, so that's the x to the 5 coefficient. So if I make a note, x to the 5 is 3402 x to the 5. It says work out the value of a in this bracket here. So what we're not going to do is two things. We're firstly not just going to manually expand the brackets 8 times, not doing that. No, but also what we're not going to do is just do the binomial expansion all the way through either. What we're going to do is just be quite selective and only work out one particular term, in particular the x to the 5 term, right? If we do the binomial expansion, we know that the x to the 5 term, if we were to just do the binomial expansion on that term, remember firstly we have a binomial coefficient, so the total power is 8, so n is 8. So obviously we have n choose r, but the power is 8, n is 8. And then the term number is 5, x to the 5, so it'd be 5, right? Then we're not x, but ax, right? Ax to the 5, because then that gives me my power of 5. Then the remaining part is the constant 2, to the remaining power of 3. 8 take away 5 is 3. So that is simply my x to the 5 term, right? Very simply. So if we were to just work that out, well then 8 choose 5 is firstly 56. That's 56. Then ax to the 5 is a to the 5 x to the 5. Then 2 cubed is 8. And then 56 times 8 is 448 a cubed, a to the 5 x to the 5. So that is the x to the 5 term, but we also know the x to the 5 term is given to be this. So actually we can compare that 3402 x to the 5 is 448 a to the 5 x to the 5. And so therefore the coefficients have to be the same. So 3402 has to equal 448 a to the 5. And so then I'd solve for a. So a to the 5 is 3402 divided by 448, which is just 243 over 32. And then to get a, then we're going to take the fifth root of that. the fifth root of 243 over 32. And so that would be simply 3 over 2. There we are. And to note, it's not plus or minus because we have an odd root. Any odd roots, like the cube root or the fifth root or the seventh root or whatever, only produces the one positive. It's when you have even roots, like 2 root, the second root or the fourth root, that gives me plus or minus. Okay, the fifth root, odd power, only one solution, 3 over 2. Okay, so here we got part B, and now using this value of A, so again, A was 3 over 2, using that value of A, find the constant term in the expansion of now this bracket here, 1 plus 1 over x to the 4 times by the same bracket we dealt with in part A, 2 plus ax to the 8. So if I jot that down then, so what 1 plus 1 over x to the 4 times by 2, add ax. What we know A is 3 over 2, so 3 over 2x to the 8. And so it wants me to find the constant term. Now constant means there's no x's, okay? There's no x involved. So, again, okay, a fairly typical sort of question, a bit harder, a bit of problem solving. Okay, so the idea is essentially, if we consider this individual expansion, which we did in part A, if we consider what that expansion looks like, kind of visualize how the two brackets multiply to get me the terms I want. So to make this quite easy to sort of visualize, this bracket here, 2 plus 3 over 2x to the 8, right, that's just a polynomial, right? If we were to expand it, right, we're not going to, but if we were to, it would look like a quadratic, a polynomial up to x to the 8. So it would look like a0, right, add a1x, add a2x squared, add ... and then the last term a8 x to the 8. And so these a's are just the coefficients, right? And obviously the numbering just correlates to the degree of the x. But yeah, essentially they're just coefficients. So coefficient and then x, coefficient x squared, coefficient x to the 8. That's what the expansion would look like, okay? Obviously we'd have to work out what all the coefficients were, but that's what it would look like. So with that in mind, hopefully you see it's just a polynomial up to x to the 8, right? So with that in mind, this expansion here then, if we want to work with this, then it would be 1 plus 1 over x to the 4, and then times by a0, a1x, a2x squared, add ... add a8 x to the 8. Now hopefully it's a lot easier to visualize how things will expand to get me what I want, and what I want is a constant. So how am I going to get a constant from doing this expansion of these brackets? Well, the way expanding brackets works really is we start with the first term, 1, in this first bracket, then that 1 will multiply by all the terms in the other bracket one by one. So it multiplies by every term in the second bracket, and then the exact same, we move on to the next term, 1 over x to the 4, and it will do the same thing. Now with that in mind, how are we going to get the constant term? Well, firstly, 1 will multiply by all the terms. So if we want to ensure we get a constant term from the expansion, so no x's, well, the 1 here will then only be able to multiply with the other constant a0, right? So actually, to get the constant, first we're going to do 1 times a0, right? And that's the only way we're going to get constant. Everything else, every other term here has an x involved. So that's a no-go. Then, the trickier one is this 1 over x to the 4. Now, if we were to multiply by the constant in the other bracket, we would have a0 over x to the 4. That's still involving an x, right? X to the 4, sorry. That's still involving x. If we then did 1 over x to the 4, times a1x, so that would be a1x over x to the 4. Again, that will cancel, but I'll still get x cubed, right, in the bottom. That's not what I want either. And hopefully you realise then that actually I'm going to need to times 1 over x to the 4 by x to the 4, the x to the 4 term in this other bracket, to ensure the x's cancel. So here there'll be a term a4 x to the 4, right? If I multiply that by if I multiply 1 over x to the 4 times a4 x to the 4, right, well that would be the x4s will cancel and it would just be left with a4, right, this coefficient a4. And so there we are. That's how we get my constants then, right? And that's how I get my overall constant term here. Now, the last problem I need to deal with is actually to find out what I can simplify this actually. It's a0 and a4. So the last remaining problem is to work out these missing coefficients here. So the a0 term, the constant term in this bracket, and the x to the 4 term here. So I'm gonna bring back my 2 plus 3 over 2x to the 8, right? That's this bracket here. And so I'm going to work out the constant term and the x to the 4 term in my in that single bracket there, which is this bracket here. So the constant term, firstly, that's going to be well, the x part has to be no x, so it has to be, well, firstly, it'd be 8 choose 0, because then the power of x will be 0. So 3 over 2x to the 0, there's no x there. Then 2 would have to be the 2 has to be a power of 8, then, right? And so if we work that out, well, 8 choose 0 is 1, anything to the 0 is 1, and so we're just left with 2 to the 8. Well, 2 to the 8 is 256. So that's that part then. Then we also need the x to the 4 term, right? So the x to the 4 term, that's going to be when x to the power of 4 now, so it's going to be 8 choose 4 when the power is 4. So then 3 over 2x, the x part of the bracket, is then power 4. Then 2 has to be a power 4 as well. And so then if we simplify all this, well, 8 choose 4, firstly, is 70. And then we got 3 over 2 all to the power of 4. 3 over 2 all to the power of 4 is 81 over 16. And 2 to the 4 is 16. And then we have an x to the 4. And so actually, if we just simplify this, we get 70 times 81 over 16 times 16, we get 670 x to the 4. So there we are, that's my x to the 4 term and my constant term. So that means then that the overall constant term from this double bracket here, as we discussed, is going to be the a0, so that's the constant part, and the x to the 4 part, right, a4. So therefore constant term overall from the double bracket, that's going to be the 256 here, added the coefficient here, 5670, and then that would be 5926, and there we are. So make sure, hopefully it made sense of how I did that by essentially just seeing that firstly this term 1 in this bracket here, I want to multiply it by the constant term a0, right, the constant term there, to get a constant, and then for the 1 over x to the 4 part, then obviously I want to multiply it by the x to the 4, because then x to the 4 divided by x to the 4 cancels out, and that leaves me with a constant as well. And so I just found the constant and the x to the 4 part, then I went from there. Okay. Question 9. Okay, we've got a sort of more standard integration question again. So we're told here to find the value of the constant k, where the integral from 9 to k of 6 over root x dx is equal to 20. So it's kind of definite integration, but kind of in reverse, where we need to find the missing limit, but we're given what it equals to. So again, k is just a number, don't freak out about it. We just do the integration as we normally do with definite integration. So we firstly just work out what the integral of 6 over root x is. Well, 6 over root x, obviously we're going to have to simplify it to write it as a power. We don't want any roots or fractions. Well, 6 over root x is going to be 6, well, x to the minus a half, right? Because that's x to a half, root x. And then it's reciprocal, so 6x to the minus a half. So that means that I've got the integral of 9 to k of 6x to the minus a half dx. Then I just integrate this. So that would be, if we were to integrate it, 6x, then minus a half, we add 1 to the power, so it'd be positive a half, then divide by a half. And again then, we add our square brackets because we're integrating between 9 and k. That's the limit's going to sub in. Well, firstly, we can just simplify this whole nasty fraction here. So this is basically 6 divided by half. If you put 6 divided by half in your calculator, you get 12. So this is 12x to a half. So it's a lot nicer. And so then I just sub in 9, then sub in k. So that's going to be 12x, which is 9 to a half. Then take away 12 lots of k to a half. Well, 12 lots of 9 to a half is 36. Take away 12, k to a half. I can't do anything more here. But actually I recognise that k to a half, anything to a half is just the root, right? So it's going to be root k, the square root, okay? So that's my final answer. And I'm told that this whole integral equals 20. So therefore I can say that 36 minus 12 root k is indeed 20. And now we just solve for k. So then 12 root k, if I add 12 root k, will be 36 minus 20. That's going to be 16. Then root k is 16 divided by 12, which is 4/3. So if root k is 4/3, then I could square both sides to get rid of the root. So k is 4/3 squared. That's going to be 16 over 9. And that is my solution for k. Okay, question 10. I've got this question here. I'm told a student is investigating the following statement about natural numbers. Natural numbers, again, that just means positive integers. So it's 1, 2, 3, 4, ... Okay. And we're told that any natural number is n cubed minus n is a multiple of 4. It says, part A, prove using algebra that the statement is true for all odd numbers. So this is a standard proof by exhaustion, right? Where we split up into odd and evens. Here we just want to find what the odd numbers go to. So odd numbers. So n, if n is an odd number, remember we can write any odd number in the form 2k minus 1. Or add 1, doesn't really matter, but add or minus 1, obviously when k is an integer as well. We can always express any number in this form here, 2k minus 1 or plus 1. So that's n. If it's an odd number, then we could say that n cubed minus n is the same as 2k minus 1 cubed, take away 2k minus 1. Then at that point we just expand. So what I'm going to do here, I'm probably going to expand, to not kind of make it messy, I'm just going to expand it down here. In somewhere down the page. So just write it out. So I'm just expanding it on its own rather than just pulling it, doing it all in one. So if I were to do this bracket first, this double bracket, 2k minus 1, 2k minus 1, that'd be 4k, 4k squared, then minus 2k minus 2k minus 4k, add 1, then times by 2k minus 1. That would be then 8k cubed minus 4k squared minus 8k plus 4k, add 2k minus 1. And actually we can simplify it to then get 8k cubed. Am I missing a term? Should that be... Yes, that should be 8 minus 8k squared. So then that'd be minus 12k squared. Add 6k minus 1. And so there we are. We could substitute that expansion into here. So then n cubed minus n. If I substitute that in, that's 8k cubed minus 12k squared at 6k minus 1 for 2k minus 1 cubed. Then I'm subtracting 2k minus 1, so that'd be minus 2k plus 1. And so at that point I could just collect like terms. So that's 8k cubed, take away 12k squared, 6k take away 2k plus 4k, and then the 1's cancel. So there we are. And actually what I can do here is I can factor a 4k out. Or what's the aim here? It's a multiple of 4. That's what I want to show. So really I want to factorise just the 4 out. So then I can say that's 4 lots of 4 lots of 2k cubed minus 3k squared add 1. So that's all a multiple of 4. Okay, so therefore n cubed minus n is a multiple of 4. Because obviously we just factored the 4 out, so 4 has to be a factor, as 4 is a factor when n is odd. And there we are. Okay, then part B, we now need to use a counter example to show that the statement is not always true. Not always true. So again, a counter example, best way to kind of pick one is think about the question. So obviously we proved it's for all odd numbers. So obviously just trying to think of an odd number won't work to disprove it, right? So let's think of an even number. Well, the first even number is 2, right? So let's try n is 2. Let's see what happens there. If n is 2, then n cubed minus n is 2 cubed minus 2, which is 8 minus 2, which is 6. But that's not a multiple of 4. No, sorry, 4 is not a multiple. Yeah, no, that's not a multiple of 4. 6 isn't a multiple of 4. Because obviously 4, 8, 12, where 6 is not in the 4 times table. So therefore, n is 2 is a counter example. And yeah, and so remember, a counter example is just an example that is where the statement does not work. Okay, that's what we did there. Right. So okay, we've got this question now. So we're told the owners of a nature reserve decided to increase the area of reserve by trees. Trees started planting on the 1st of January 2005. The area in 8 kilometers squared, and C is a constant, and T is a number of years. So literally all I'm really doing is just underlining the units and the variables pretty much. I can figure anything else out if I need to as we go along. Okay, so first of all, part A, it says find the area of the nature reserve that was covered by trees just before tree planting was started. So A, the equation was 80, take away 45, e to the ct, so this constant c. So the area A, the area when it was just before it started, I'm pretty much talking about the initial time when t is 0, right? So simply substitute t0 into here. So at t0, A is 80, take away 45, e to the 0 effectively, right? And e to the 0, anything to the 0 is pretty much 1. So this is basically 80, sorry. Take away 45, that's a 1. So that's 80 take away 45, which is 35. And so that would be the area meters squared. Okay, that was my... Oh, was it kilometers? No, it's kilometers, sorry. Kilometers squared. There we are. There's my units. Okay, then I'm told on the 1st of January 2019, an area of 60 kilometers squared was covered by trees. It says, use this information to find a complete equation to the model, given the value of c to 3 significant figures. So, complete equation basically means you need to find any missing values. So here's c. So if I restate what a is, capital A, is 80 take away 45 e to the ct. I need to find c here. Well, I'm giving some information. On January 2019, now that's a year, that's a value of t. But what value of t will that be? Well, actually, t starts at 2005. So how many years have we gone from 2005 to 2019? 14 years, right? So that means t is 14 here. From 2005 to 2019. The area is 60, so a is 60. So that's a condition, that's a value I could sub in. So a is 60, t is 14. Which means 60 is going to equal 80. Take away 45 e to the 14c. And so if I then subtract 80 from this, I get minus 20 is minus 45 e to the 14c. So then e to the 14c is minus 20 divided by minus 45, which is 4/9. So now I've got to solve e to the 14c is 4/9. And what I can do here is I can simply just take log for both sides, take luns. So log base e of e to the 14c is ln of 4/9. And so then I can use my power law, my log law, so the power comes to the front of the log. So 14c, lots of ln e, is ln 4/9. Well, ln e goes to 1, right? Log base e of e goes to 1. So 14c on its own equals ln 4/9. So therefore c is just a 14th ln of 4/9. So that's the value of c. To 3 significant figures then, if we put that on the calculator, if we put 14th of ln 4/9, that's minus 0.0579 to 3 significant figures. So therefore my model is my final full model is a is 80 take away 45 e to the ct, so e to the minus 0.0579t. And so make sure you do restate the model at the very end here with the value of c included. You might lose a mark because it says to find a complete equation. So once you found c, you need to then state the equation again with all the values written down. Okay, there we are. Then it says on January 2020, the owners of the nature reserve announced a long-term plan to have 100 kilometers of the nature reserve covered by trees. Right. What's talking about here is it's talking about a long-term plan. Long-term is the key phrase here. That is talking about when t goes to infinity, when t gets really large. Okay, when t gets really large, you want the area to be 100. Now, if we look at our model, part C, if we look at our equation here, our model, you should remember that when t goes to infinity, right? The exponential, when it's a negative exponential, which we have in this case, the exponential will go to 0, right? If the exponent goes to negative infinity, which it happens here, negative infinity, e goes to 0. So again, think about the e to the minus x graph. E to the minus x, it goes to 0, right, in the long term, right? So you need to remember that for anything to deal with long-term behaviour, or when t goes to infinity, or t is very, really large, the exponential goes to 0. So when the exponential goes to 0, we have 80 take away 45 of 0, which is 80. So that's telling me that essentially the most a can be is 80. In the long term, a can only go up to 80 kilometers squared of area, which means 100 kilometers squared isn't in the possibility according to the model. So I'm going to say the model predicts model is not reliable. What was the phrasing they used? Appropriate. Okay, it's not appropriate. Okay, it's not appropriate as it predicts the long-term area will only go to go up to 80 kilometers, not 100. Okay, and there we are. So yeah, again, usually 1-2 markers, as you can see here. Any exponential, if it's talking about if you're talking about going to infinity, you're pretty much going to need to set the exponential to 0, okay? Because as you can see with the exponential graph, it will go to 0 in the long term. Okay, then question 12. We need firstly to solve for 0 to theta to 450 degrees the equation 5 cos squared theta equals 6 sine theta, and again it's between 0 and 450 degrees. So this is a standard trig equation, right? So the first thing to notice is I have sine and cos. So I can't really solve it at the moment. I can't factorise anything either. So if I can't factorise anything, I'm probably going to have to resort to maybe using trig identities and cos squared. The identity sine squared and cos squared equals 1 stands out to me. Okay, so again you need to remember the identities sine squared, cos squared is 1, and also tan is sine over cos, which are not in the formula book as you saw earlier. So the cos squared screams this identity, so let's substitute that in. So then that would be, if I rearrange for cos then cos squared is going to be 1 minus sine squared, which means the equation will become 5 lots of 1 minus sine squared for cos squared. That would equal 6 sine theta. If I expand here, I would get 5 take away 5 sine squared theta equals 6 sine theta. Then if I move the left to the right side, if I add 5 sine squared, I get 5 sine squared theta, add 6 sine theta, take away 5 equals 0. Now this is another disguised quadratic, but now I can say u is tan theta, no, sine theta, sorry. Then if u is sine theta, then u squared is sine squared. So that means 5u squared at 6u minus 5 equals 0. And so then I could just solve this quadratic for u. So if I just state the formula, so minus 6 plus the minus the root of 6 squared minus 4 lots of 5 of minus 5 over 2 lots of 5, just to state my working fully to get the solution. So if I solve that, then I get, that's interesting. One decimal place. Okay, so I'm going to round my answer because it's not a nice fraction. So U is either 0.566 to 3dp, or U is equal to negative 1.766 to 3 decimal places. So those are my two solutions. But of course I want to solve for theta, not U. So if U is sine theta, that means sine theta is 0.566, or sine theta is minus 1.766. Okay, right. So, okay, I need to solve these individually. So firstly, if sine theta is 0.566, then if I do inverse sine of that, inverse sine of 0.566, I get 34.47 degrees to 2 decimal places. But of course, there'll be more solutions, right? If I were to sketch the sine graph, say down here, let's say for 360 degrees, then obviously 34 degrees, 34.5 is going to be somewhere there. So then the next solution, very similar to the earlier question about the parallelogram one with the ambiguous case. Again, we use symmetry around the top of the peak of the curve here. Either end is the same. So the end here is 34.5, is the same end between this next solution here and 180 at the other end of the curve. So that means if you can spot that, the next solution is going to be 180, take away this 34.47, which is 145.53 degrees to 2 decimal places. Right. But of course, our interval is between 0 and 450. So it's a bit more than 360. So we're going to need to maybe consider adding on. So if we got these are my two main solutions, right? So if I want to find if I want to find more solutions, I need to add on. I need to add on 360 to all my solutions. So as a reminder, theta is 34.47, then 145.53. Then I need to add on 360 to my solutions each time, because obviously it repeats every 360 the sine graph. So once I've got my two main solutions, I add on 360. So 34.47 add 360 is 394.47. Then if I add 360 onto 145, then add 53, I get 505.53. Now what is the problem there? Well, it can only go up to 450. So actually that is outside the range. So these are my only three solutions here. Okay. So that's that equation. Now we need to solve sine theta is minus 1.766. Now actually, you might be able to spot there are no solutions, because again the sine graph is only between 1 and minus 1. Minus 1.76 is somewhere down here. That doesn't ever touch the curve. So there are no solutions here. So sine theta cannot be minus 1.766. So no solutions here. So that means in general the only solutions come from my first equation here. So theta to 1 decimal place is 34.5, 145.5, and 394.5 to one decimal place. And that is my solution. Oh, okay, there we are. Then part B. And also, if you didn't spot that, that's fine. If you did inverse sine of minus 1.766, you'd get a math error. So you know there's something not right there. Okay. Part B, we're given some working. And we're told a student's attempt to solve the question 3 tan x minus 5 sin x is 0 between minus 90 and 90. They've done some work. They've done some working. So there are two ways you can approach this. If you could try and solve it yourself and then compare what the student done at the end. It might be a bit more simpler that one, clearer that way. But if you're a bit more, I guess, confident, then you just literally look at the working, go line by line, and think, does that make sense? Let's go with that approach. So here we obviously start with the equation. So then we jump to the next line where they've done sin x over cos x. That makes sense because tan x is indeed sine over cos, right? We know that identity. So that's right. Then they appear to multiply by cos x to everything. That's fine. You can do that to get rid of the fraction. That's fine. What have they done from this step to this step then? They seem to divide it by sine. Oh, that is a bit of a problem. You should never ever... No, what you should do is always try and factorise whenever you can. If you can't, then divide. But actually, we could have... you shouldn't divide by sine here. So we have 3 sin x minus 5 sin x cos x equal to 0. I can factor a sine out, so I can do sine of 3 minus 5 cos x equal to 0. So what happens is, if you're dividing by sine, you're missing out the solution sin x is equal to 0. So the first error is going to be essentially he divided by sine instead of factorizing. So that's wrong. You can't jump from that to that. You should have factorized instead, because then you missed out the solution from sin x is 1. So missed solutions from sin x equal to 0, sorry. Okay, then they appeared to rearrange the equation to solve for cos x. It is 3 over 5. That's actually correct, because then 3 is equal to 5 cos x. Divide by 5, you get 3 over 5. Then they got this solution. So I presume they did inverse cos. If we did inverse cos of 3/5, you do indeed get 53.1, right? That is actually correct, that solution, but what is incorrect is that it's not the only solution. So this last step is wrong. Why? Because remember, it's between minus 90 and 90. So, okay, so if I were to roughly solve that equation here, so cos x is 3/5. Then obviously, if we did inverse cos, you get 53.1. That's great. If we were to then consider the cos graph, it would look like this. But of course, we're going from we have to go from minus 90 to 90. So if we go minus 90 there, so 53.1 is going to be somewhere there. But actually, if we read off the graph, there is actually another solution possible between 90 and minus 90. It's here. And actually, it's symmetrical again in the middle of the hump. So that would be minus 53.1. So the other error is that the other solution is minus 53.1. So they missed that out. So if I were, the second error is going to be missed out the solution x is minus 53.1. Okay, from obviously cos x is 3/5. So that is the two errors. Okay, there we are. Okay, then it says for the next part, we're told the first four positive solutions in order of size to the equation cos of 5 alpha at 40. I'll make a note of that. Cos of 5 alpha at 40 degrees is equal to, what's it, 3/5 again, is it? Yes, 3/5. The first four positive solutions are alpha 1, 2, 3, and 4. Find alpha 4. Okay, so we need to find the fourth positive solution. Okay, fourth positive. So again, let's just proceed by solving this, right? So if I were to solve that, so again, if I did inverse cos of 3/5 of so the angle we get is 5 alpha at 40. So if we did inverse cos of 3/5, then the angle is 53.13, two decimal places. And so we want to solve for alpha, right? So we kind of need to rearrange. But obviously it's talking about the first four solutions. So what we need to do, this is the first solution. We need to then find more. So then if we were to proceed to find the next solution, again, if we look at our cos graph, it will be minus 53.1. If we add on 360 then to minus 53.1, or actually alternatively what you could do, again, if we use the cosine graph, we know the first solution is 53.1. Or 53.1. So then the next solution you could spot alternatively, instead of going backwards, you could see it's here. And then again, it's symmetrical in the middle, so either end from 0 to 53.1 is the gap is 53.1. It's the same distance from this next solution, right? And then the other end at 360. So that means to get the next solution right, it's 53.1 degrees away from 360. So it's going to be 360, take away 53.1. Well, 1,3, right? And so that next solution is going to be 306.87 rounded. Okay, so those are my two main solutions. And obviously the graph will continue on every 360, so we just add on 360 from here. So the other solution, if we add on 360 to 53.13, we get 413.13, or obviously then we add on 360 to the next solution, so 306.87. We get 666.87. And so I suspect that this is going to be alpha 1, this is going to be alpha 2, alpha 3, and then this is going to be alpha 4. So this is going to be the important one, alpha 4. Okay, so right, so obviously we know that 5 alpha 40 equals these solutions. So okay, so if we were to then subtract 40, so 5 alpha, if I subtract 40 to all these solutions, 53.13 take away 40 is 13.13. Then take away 40 to 306, that'd be 266.87. Then 413 take away 40 is 383 or 73, is it? 373.13, and then 666.87 divided by take away 40 is 626.87. And so then we can spot that this is going to be the fourth solution. But so then for alpha 4, this is going to be the fourth positive one, right? The fourth one in the list. Then alpha 4, so 5 alpha is equal to all of these solutions. So to get alpha, I need to divide by 5 lastly. So if I divide this by 5, 626.87 by 5, I get 125.4 to 1 decimal place. I believe it wanted it to 1 decimal place. Yeah, oh, to the nearest degree. Okay, so to the nearest degree means I need to round it to like the nearest integer essentially. So that would be 125, just 125 degrees, nearest degree. Okay, so there we are. Right. So hopefully it made sense, right? I didn't need to then divide every solution by 5. You could do. It's unnecessary because at this point here, once I spotted that these were the first 4 positive solutions, divided by 5 makes them positive. So I only needed to focus on this 4th solution here because that's alpha 4. Okay. So then I divided just that one by 5. Okay, and that gets me that solution here. Okay, cool. Okay, question 13. I am given a log graph. So log, right? Logs on my graph. So what we're told here is the resting heart rate of a mammal measured in beats per minute is modelled by the equation h is pm to the q. Right, so if I make a note of that, h is pm to the q. P and q are constants, and m is the mass of the mammal. I'm told that figure 2 shows a linear relationship, linear meaning a straight line, essentially, between log h and log m, which we'll see here again, right? I'm told that the line meets the vertical axis at 2.25. I can see that, right? And also the gradient is minus 0.235. Then it says to find the value of P and Q. So actually, if you practice enough of these sort of questions, these are linearization questions. These are like using logs to convert into straight lines. So if we're going to use logs here, so we start this equation, right? We want to find P and Q. We can take logs. So log H is log PMQ to the Q. Again, log, if I'm not specifying a base, it's log 10. Okay, but anyway, so take logs. Then what I can do is, again, I can split up this product here. This is P times M to the Q. So I can say log H, using my log laws, is log P, add log P M to the Q. Then the power Q comes to the front. So then log H is log P, add Q log M. And I can rearrange this a little bit to then log H is Q log M, add log P. And so what we've got here is log H and log M. But we've also got the equation log H and log M here. So actually, if I compare, right, with a straight line, this, if I call that big H, and then I'll call that big M, or big M, actually no, I won't call it that, it might be a bit confusing. Hopefully you recognise that essentially, let's say this is Y and this is big X, right? Because obviously, log H is on the Y-axis, pretty much, right? And log M is on the X-axis. Then actually this is Y is equal to M. If I call QM and this log P, this number C, this is in the form Y is MX plus C. And hopefully you can then see that my gradient would have to equal Q. And also the intercept would have to equal this log P at the end. Well, actually, I am given the gradient and the intercept. The intercept is 2.25 and the gradient is minus 0.235. So that means, therefore, Q, the gradient is minus 0.235. That has to be Q. And also the intercept, the log P, I'm told the intercept is 2.25, right? 2.25. So I equal log P to 2.25. Then to solve for P, again, that's log 10p. So I can raise everything by 10. So 10 to the log 10p is equal to 10 to the 2.25. Here, the base 10 cancels with log 10. You can think of it as an exponential cancelling with the log because it inverses. So p is 10 to the 2.25. And so if I put that in a calculator, I get p is 177.83. What's my rounding going to? 3 significant figures. Okay, so that would be 178 3 SF. And Q is 3 SF anyway. And so there we are. That is the values of P and Q there. Okay. Okay, cool. So again, very standard approach. Take logs of the equation and then compare with a straight line to find the gradient and the intercept. Okay, then it says a particular mammal has a mass of 5 kilograms and a resting heart rate of 119 beats per minute. So again, remember the mass is m, so that means m has to be 5 here. Also, resting heart rate, that is h. So h is 119. Now, that's relating to the model, to the equation up here, right? H is pm to the q. So if I remind you, h is pm to the q, but we know what p and q are now. H is p, so 178, m to the minus 0.235. So we've got these two stats. Then it says comment on the suitability of the model. Well, let's just we got this result, right? So m is 5, h is, when m is 5, h is 119, right? So simply, let's just set m is 5 and let's see what happens. At m is 5, h using the formula, the model, right, is 178m, which is 5, to the minus 0.235. If I put that in the calculator, hopefully it's close to 119, right? So 178 of 5 to the minus 0.235 is 121.9 to 1 decimal place. That's actually pretty close, right? 119, 121.9. That's pretty close, I'd say. So the suitability is, given that bit of information, right? Given that information, it matches with what they said. It matches with reality. Well, what happens when the mass is 5? It's 119. Well, we've got 121. That's pretty close. So it's suitable, right? So 129.1 is close to 119. So model is suitable. So model is suitable as it gives a close approximation to resting heart rate when mass is 5 kilograms, right? There we are. Okay, then it says for part C, with reference to the model, interpret the value of P. So key exam word again, interpret means, explain what it means specifically in the scenario they've given. So specifically in the scenario about heart rates with a mammal with a certain mass. Okay, So what does P mean? So again, if I remind you of the model here, H is PMQ, right? Right. So, the way to think about these is kind of what happens with certain values, I guess. So, would it be initial value of M, right? If M was 0, then H would be P lots of 0 to the cube, right? But of course, anything times 0 is 0, so H is 0. That tells me nothing. It tells me when there's no mass, there's no heart rate. I mean, nothing surprising there. So actually, the significance of P arises when you consider M is 1. If M is 1, then H is P lots of 1 to the cube. Now 1 to the anything is just 1, so H is P. But obviously we know what P is. P is again 178. So H, that's 178. That tells me sort of like when the mass is 1. So specifically the mass of a mammal. So when the mass of a mammal is 1 kilogram, what happens here is the resting heart rate H is 178 beats per minute. BPM, beats per minute. So that's what that means. It's sort of like a sort of a sort of standard initial sort of value. Obviously, it's not initial because obviously it's not M is 0, it's M is 1. But that's kind of what it means, right? A certain value, hopefully you can see here. Obviously, the mass is 1, a sort of simple number. It gets me exactly 178, which is P. So that's what that means, right? Just literally describing the result here in relation to what H and M represent. So M, the mass of the mammal, H, the heart rate, right? Okay. Okay, alright, we got this question now. So we're given a curve y is f of x. F of x is minus 3x squared at 12x add 8. We need to write f of x in this form here. And what is this form? Hopefully you recognise this is completed square form. Right? Any quadratic that basically just has one factor of x squared, like this, just one bracket squared, that's completing the square. So, let's do it down here. F of x is minus 2x squared, 3x squared, add 12x add 8. If we were to complete the square, again, what we do is here, let's factor the minus 3 out of the x, so minus 3 of x squared minus 4x, right? Because then minus 3 times minus 4 is 12. The constant plus 8, we just leave it because we're not going to do anything with that, really. The completing the square, now we're going to do here with the x's, right? So, minus 3, then if we complete the square inside here, that's going to be x. Then a half of minus 4 is minus 2, all squared. Then take away 2 squared is 4, so take away 4. Then we add the 8 outside. Then we can expand. So then that's going to be minus 3 of x minus 2 squared. Minus 3 times minus 4 is plus 12, plus the 8. Then lastly, that is minus 3 of x minus 2 all squared, add 20. And that is in the form there. Then it says part B, we're given the curve has a maximum turning point at M. You can see that here, right? It's the maximum point. It says find the coordinates of M. Now, with completing the square, we can find, we don't have to differentiate in this case, because when we complete the square, to get the turning point, what we do here is we set the bracket to 0. So x minus 2 is equal to 0. So then x is 2. And so what we're left with when the whole bracket's 0, we're left with, if this is y, right, the function y, then we're just left with 20. So y is 20, which means the point M is x is 2, y is 20, okay? The whole idea being that obviously the maximum point, obviously, when the bracket, because it's a square bracket, it has to be at least 0. If we times in a positive here by a negative, it's always negative. So the best case scenario from a negative is to just make it 0. So if you set it all of this to 0, then we're just left with 20 at best. Anyway, so that's completing the square. So actually I can add that point on. So m is 220. Yeah. Okay. Now I'm given the graph here. I'm given a sketch of the curve, and I'm also given this line L here through M, and it's parallel to the x-axis. Blah blah blah. The region R, as you can see here, is there. That's the region. We need to find the area using integration. Okay. So right. So to find the area then. Right, again, with this sort of, when we're dealing with lines and curves, it's best to split up the area into two different sort of pieces, right? Well, firstly, the region is below the line, right? So actually what we have here, the region is firstly between 0 and m. Well, x is 2, right? X is 2. So that's the limits of x, right? That's where we're going to integrate between, if you will. But actually then, with that in mind, the region is then bounded between the line and the curve, right? So what we've got here is essentially, if I use a different colour, let's say blue. Firstly, you can consider the area of R as the area under the line between 0 and 2, which hopefully you recognise is just going to be this rectangle here. Or, if you didn't spot we have a rectangle here, then the area under the line, right, area under the line can simply be computed by the area under the line here, could be computed by the integral from 0 to 2 of the straight line. Well, we're not given the straight line equation, but we can easily find it because it's going to be a straight line. So it's going to be a horizontal line. So y, well, we know at this point m, y is 20. So that's the equation of the line. So y is 20. So what you could do here is just literally integrate 20, right? That's a constant, that will go to 20x. And then we integrate between 2 and 0. Those are my limits. That gives me the same area under the this straight line here. Okay. So the area is going to be the area of the rectangle between 0 and 2. So the length is 2, right? The length is 2. And then actually, if I have this whole blue area, right? If I take the area under the curve, which I do in red, right? The area under the curve in red, right? Then actually, the only bit of blue area is indeed the region R. So alternatively, I can take the whole rectangle away from the area under the curve between 0 and 2. Right? So what essentially I've got here is, to find the region R, I essentially split it up into two different areas, where the area of the rectangle here in blue take over the area under the curve. So the area of R is area of rectangle take away area under curve. Okay, so the rectangle then, as you can see here, it's this rectangle here. Obviously we know it's 2, right, on the x-axis, because it's between 0 and 2 here. But then what about y? What about this sort of height? Well, actually we also know the y coordinate is 20. So then that means it has to be 20 up. So the area of the rectangle is simply going to be 2 times 20 then, right? Which is 40. Then we need to deal with the area under the curve, which is the harder bit, right? So the area under the curve then, well, if I get rid of this whole rectangle stuff, this obviously this area under the curve from 0 to 2, that's just going to be the integral then. The integral of the curve between 0 and 2. Well, what's my curve? Again, remember my curve is minus 3x squared, add 12x, add 8, I believe, dx. Yes. Okay. So that, to work out the area under the curve then, is simply this integral here. So just work out this integral here. So then if we integrate, again, our square brackets, because we're going to be including the limits. So minus 3x squared, that'd be minus 3x. Then add 1 to the power, that'd be cubed. Then divide by 3. Then add 12x. So 12x, x has a power 1. Add 1 to that, we get 2. Then we divide by the power 2. Then 8. Any number, just we add an x on. So 8x. Between 2 and 0. Then we can just sort of simplify the fractions, right? If we simplify the fractions, well, minus 3 over 3 here, firstly, just goes to minus 1. So we get minus x cubed. Then 12 over 2 here just goes to 6. So 6x squared. And then 8x. So it's a lot nicer. So we integrate between 2 and 0. So we're going to sub in 2 first. So it's going to be minus 2 cubed. Add 6 lots of 2 squared. Add 8 lots of 2. Then I'm going to take away, plug in 0. So minus 0 cubed. Add 6 lots of 0 squared. Add 8 lots of 0. If we put that in the calculator then, we get 32, right? So that means then the area of the region that we want, which was shaded to us, again, as we discussed, it's the area of the rectangle, the area under the whole line, right? Under the whole line from 0 to 2, which was 40. Take away the area under the curve of 32. So 40 take away 32 is 8. And you could specify units squared, right? We don't know what the units are, it's a graph, but squared means obviously it's an area measurement, like centimetre squared or metre squared or something like that. So that is my final answer. Cool. Okay, this question here, question 15. So I'm given figure 4, which shows a sketch of a circle with a centre N, which is 7, 4. I'm given the line L with equation y is a third x. And it's a tangent to C at the point P. You can see that, right? It's just touching the circle at that point. I first need to find an equation of the line Pn. So that's going to be this tangent line here. The radius line at Pn here. So y is mx plus c. Okay. So y is mx plus c. That's the equation of any straight line. So firstly, m, my gradient, right? Well, actually, you should remember the circle theorem that a radius is perpendicular to a tangent. But actually, we know what the gradient of the tangent is. The gradient of tangent is a third, right? Just by looking at the line of the tangent given, the gradient is a third, right? Which means the gradient of the radius here is perpendicular. It's a perpendicular, right? So therefore, gradient of the the gradient of the radius is going to be minus 3 as it's perpendicular, right? So then we can start to fill in my equation of the line. So y is now minus 3x plus c. So now I just need to find c. Well, I also know that this point N, the centre, is also on this line Pn, right, on the radius. So I can sub in the 0.74 in. to sub 7, 4 in. So x is 7, y is 4. So y is 4 equals to minus 3 lots of 7, add c. So 4 is minus 21, add c. So that means c is 25. And therefore my final equation is y is minus 3x plus 25. And there we are. Cool. And then it says, part B, find an equation for the circle C. So an equation of a circle, again in general, is x minus a squared and y minus b squared equals r squared. So we need a centre positive a, positive b, and the radius r. Those are the two ingredients we need. Well, actually, for the centre, we already are given that n is the centre, right? We're told centre n 7, 4. So actually, if it's 7, 4, centre is n equals 7, 4, then I can start again to fill in my equation of the circle. So that means x take away 7 all squared, and y take away 4 all squared is r squared. Okay, then lastly I just need the radius, but obviously it's going to be a bit harder than the centre, obviously, because we're not given the radius and it's 4 marks. But how can we find the radius? Well, obviously the radius is, well, not the radius, the radius, the length of the radius, right, is obviously the length of the line from n to p. I'm given the coordinate n, but I'm not given p. P is xy. I don't know what the point is, but I can work it out, because now if I get rid of this here, I also have the I found the equation of the radius of Pn, right? It was y was minus 3x at 25. So the intersection point P I can find by equating the two lines together. So tangent and radius meet at P. That means that therefore the equation of the tangent, which was a third x, and the radius, which was minus 3x at 25, these two lines, right, the tangent, again remind you, the tangent is a third x and minus 3x at 25 for the radius. Those are the two lines. We're going to intersect them as simultaneous equations. So third x for y equals minus 3x at 25. If we solve that for x, then a third add 3x, that's going to be 10 thirds. X, that's going to be 25. And so therefore x then is going to be 25 divided by 10 over 3. And so that would be 15 over 2. Of course, that's my x coordinate, so y, then I need to find the y part. Again, I can just substitute that into either equation here. Well, obviously, this is going to be the more simple one. Y is a third x. So y is a third x, which is a third of 15 over 2. And so that would be 5 over 2. So P is the point 15 over 2 for x, 5 over 2 for y. So length then, the length of the radius, right? The length of the radius, in other words, the distance from P to N. So I've got the 2 points now. I know that P is 15 over 2 and 5 over 2. And I know that n was given to me in the question. N was 7, 4. So that means the length Pn, so remember P is 15 over 2, 5 over 2. N is 4, 7, I believe. No, 7, 4, my apologies. 7, 4. So the length then, the distance between the 2 points, is again just going to be the distance formula. So it's going to be the root of the change in x squared of the 2 coordinates. So 7 take away 15 over 2 squared. Then changing y squared. So 4 take away 5 over 2 squared. If I put that in the calculator, that would be root 10 over 2. So the radius then is equal to root 10 over 2. So then the radius squared, r squared, is going to be root 10 over 2 all squared, which would be 5 over 2. So there we are then. So therefore my final equation is, if we look here, where did we do it? Here, right? X minus 7 squared and y minus 4 squared is r squared, which is 5 over 2. And there is my equation of the circle. There we are. Oh, right. Then it says the line with equation y is a third x add k now is also a tangent to C. Find the value of k. There are many ways you could approach this, actually. Quite a tricky part, right? One of the trickier parts of the paper. So okay. So as we discussed, this was y is minus 3x add 25. That's the radius. Now, what do you notice is the tangent here was a third x. It's the same gradient. It's still a third x add k. So what's happening, if we were to draw a line with the exact same gradient to the circle, another tangent with the same gradient, it would look probably something like this. Obviously, I'm not using a ruler, I probably should do. It looks something like this. It will instead touch the circle here, right, at this other point here. I'll call that Q, right? So this y is a third x add k. Obviously, that's going to be k there. That's going to be a tangent to the circle at this other point Q. Now, there are many ways you could approach this. Now that we were given the equation of the circle, right? In part B, we worked that out. It was, what was it, x minus 7 squared and y minus 4 squared is 5 over 2. What you could do, the safe way, is to substitute the equation of the tangent here. So y is a third x add k. You could substitute that into the circle equation, then use your sort of common strategy of then utilising the fact that the discriminant would be equal to 0 because of the tangent, so it'd be one root, one intersection point, and then you could solve for k, sorry. You could do it that way, but that would be quite a lot of work for 3 marks. 3 marks here. What you could instead spot is, actually, because again the gradients are the same, it's still going to be perpendicular to the exact same radius. So if I just continue the radius on, p to n, now actually p to q, it'll still be perpendicular. So the same line that we worked out in part A, p to n, the same line from minus 3x and 25, is still going to be perpendicular to q. What's more is that actually n is, because it's a centre, right? It's a centre. It's the midpoint of PQ, right? Because obviously P to Q is a diameter. Hopefully you can spot that, right? P at one end of the circle, Q at the other end. It passes through the centre, so it's a diameter. And N, the centre, is the midpoint, right? That's a circle theory. That's a fact. Obviously, the midpoint of the diameter is the centre. So let's state that here. PQ is a diameter. n is the midpoint. Now, I know what n is. N is 7, 4. I also know what p is. P we worked out in part B was 15 over 2, 5 over 2. But we don't know what q is. What's q? So what I'm going to say is q is just xy, right? We can find q because we can utilise the fact it's a midpoint, right? N is the midpoint from P to Q. How do we work out a midpoint? Midpoint is the two x's added together, right? Divide by 2, and the two y's added together, divide by 2. So in this case, PQ, the midpoint of PQ, well, 15 over 2 for P, add x for Q, divide by 2. And then for Y, 5 over 2 from P, and then Y, just a Y for Q. We don't know what Y is, but Y over 2. And that's the midpoint, but we also know N is the midpoint, so that equals 7, 4. And so actually, very quickly, we can then compare and say that 15 over 2 add x over 2 equals 7. If we times by 2, then 15 over 2 add x is 14. So x is 14 take away 15 over 2, which is 13 over 2. Likewise, the y part, so 5 over 2 add y over 2 equals 4. Therefore, 5 over 2 add y is 8. If you times by 2, so then y is 8 take away 5 over 2, which is 11 over 2. And so there we are. I've got my x and my y coordinate for q. So 13 over 2, 11 over 2. Now, why is that important is we're pretty much done now because we've got a point Q, right? Q, which was, what is it, 13 over 2, 11 over 2? We got a point on the line. We got a point on the line, right? We can just substitute that point in to find K. So I'm going to sub that point in. So I'm going to sub Q into that line. Y is a third x of K to find K. And so therefore, if y is 11 over 2, then a third of x, which is a third of 13 over 2 at K. If we expand that bracket, if we do a third times 13 over 2, that would be 13 over 6 add K. And then simply, if we then subtract by 13 over 6, we get K to be 11 over 2, take away 13 over 6. We get 10 thirds. And that is K. There we are. And there might even be probably better ways than that, more efficient, better ways than that. But say that's one way. That is one way. The safer way, again, if you were to essentially solve the simultaneous equation with the circle and this tangent to find K. Obviously, it'd take a lot of work. You'd have to expand a nasty bracket. You'd probably get there in the end, though. But yeah, that's another way you can solve that. Okay, cool. Right, we've got this final question now at the end of the paper. So we're given a curve. F of x is a x cubed add 15x squared take away 39x plus b. So obviously we've got some missing numbers a and b, but we're given some information. We're told that the point 210 lies on C, and also the gradient of the curve at 210 is -3. We need to basically find the values of a and b essentially. So okay, let's just work with these two bullet points in turn. So part A. Well, firstly, we've got the point 210, so I'm going to sub that in, essentially. So I'm going to sub 210 into f of x. If I do that then, well, f of x is 2, so f of 2 is then, if I plug 2 for x in, that's going to be a lots of 2 cubed, add 15 lots of 2 squared, minus 39, 39 lots of 2 add b. So then that would be, if I simplified it, that'd be 2 cubed is 8, 8a, then 15 lots of 2 squared, minus 39 lots of 2 is minus 18. And then plus b on the end. And I also know that f of 2, when x is 2, y is 10. So it equals 10. Therefore, 8a minus 18 and b equals 10. Then if I add 18 to both sides, I get 8a and b is 28. Okay, that's one equation. I can't do anything with that. I can't do anything with that alone. But I'm also then told that the gradient at that point is minus 3. Well, gradient, how do I deal with that? Anything to do with gradients really is dy dx or f dash of x. It's the same thing. It's the gradient function. So I'm going to need to differentiate. So f dash of x then. So again, remember f of x is here. Ax cubed 15x squared minus 39xb. So if I differentiate then, obviously term by term, ax cubed, the power comes to the front. So 3 comes to the front, so it'd be 3a. X, then we knock 1 off the power. 3 minus 1 is 2. Then 15x squared, that will go to 15 times 2, that'd be 30x. And then minus 39x just goes to minus 39. And the b, just the number, no x, so it just goes to 0. That's my derivative. Then I'm told the gradient at 210, the gradient at that point is minus 3. Which means when x is 2, the gradient is equal to minus 3, right? Minus 3. So, I'm just going to plug in x is 2 in then. So then f dash of 2, f dash the gradient at 2, if I plug 2 into here, okay, so obviously here we've got 3a, so 2 squared is 4, 4 times 3 is 12, so it's going to be 12a, and then 30 lots of 2, take away 39 is 21. Right, again then, and I'm told that the gradient was minus 3, right, the gradient was minus 3. So 12a add 21 equals minus 3. So if I solve for a, 12a is going to be minus 24. A is minus 24 divided by 12, which is minus 2. Well, what do you know? We've shown that it's minus 2. Okay, then it says find the value of b. Well, we've already got an equation actually here, right? We've got 8a and b is 28, right? So I can use that to solve for b. Well, I know what a is, so that means 8 lots of minus 2 add b equals 28. So that's going to be minus 16 add b is 28. So therefore b, if I add 16, I will get 44. So there we are. A is minus 2 and b is 44. Cool. Right. That's the first part. Then it says, hence show that C has no stationary points. So again, stationary points, that is where the gradient is set to 0 in particular, right? But we worked out the gradient, right? We know what f dash of x is. F dash of x is equal to, we worked out the derivative in part A. The derivative here, the derivative was 3ax squared add 30x minus 39. So we don't need to differentiate again. We've already did the hard work. but we know that a is minus 2, so actually we can sub that in. So then that would be 3 lots of minus 2x squared, add 30x minus 39, which is minus 6x squared, add 30x minus 39. Okay, so when f of x, when f dash of x is set to 0, because then obviously that gives me my stationary points, if there were any, there that means that minus 6x squared and 30x minus 39 is set to 0. This is a quadratic equation. Now, I don't need to fully solve it, because, think about it, I want to show that there's no stationary points. That means if there are no stationary points, that has to mean that this quadratic equation has to have no solutions. How can we show, without solving it directly, that a quadratic has no solutions? We can use the discriminant, right? If we were to calculate the discriminant here, b squared is 30 squared, take away 4 lots of a, which is minus 6, and then minus 39 from c. If we work that expression out, 30 squared minus 4 of minus 6 of minus 39, we get minus 36. But hang on, that's negative. You should remember that when a discriminant is negative, there are no real solutions to this equation then. Hence, no values of x for when the gradient is set to 0, therefore no stationary points. And there we are. Okay, cool. Part C. Quite a long question this is. Part C, we need to write f of x in the form of x minus 4 and q of x. And this q of x is a quadratic expression. So, again, f of x is ax cubed. Let's do it down here. F of x is ax cubed. Add, what was it? 15x squared minus 39x plus b. But of course we know what a and b are. A is minus 2, b is 44. So that would be minus 2 x cubed, add 15x squared minus 39x plus 44. Now I want to the question wants me to write f of x in this particular form here, x minus 4 and q of x, right? So so that's equal to the factors x minus 4 and then q of x. But I'm told that q of x is a quadratic, so it's going to be ax squared and bx plus c, right? A general quadratic term, so it's going to be ax squared. I'm going to use capital A because I don't want to get confused with the little a and b I've used so far. So it's big A squared and big B and c. Right, so at that point then, I just need to find the values a, b and c. So what I can do here, there are two ways you can approach this. At this point, you could either divide this f of x is cubic. I could divide it all by x minus 4. Then that gets me the quadratic directly. Okay. Alternatively, what I can do is comparing coefficients. So if I were to expand this bracket instead, I would get ax cubed add bx squared add cx minus 4ax squared minus 4bx minus 4c. And so at this point, then all the powers of x have to match. So firstly, minus 2x cubed has to be equal to ax cubed. So that means minus 2 is a. Then again, 15x squared, the x squared has to match. So 15x squared, we've got bx squared minus 4ax squared. So 15 has to equal b minus 4a, but we know that a is minus 2. So 15 equals b minus 4 of minus 2, which is plus 8, right? So 15 is b at 8, so therefore b, if we subtract 8, is going to be 7. Then lastly, to find c, well, we could either then compare the x's, but it's a lot more simpler to then just actually compare the constant number at the end. So that also 44 has to equal the minus 4c at the end here. So therefore c, if you divide by minus 4, is minus 11. So therefore f of x then, this cubic, is equal to x minus 4, and this quadratic, a is minus 2, x squared, bx, which is plus 7x, and c, which is minus 11. There we are. Okay, and then for part D, the last part of the question, it says hence, and again this keyword hence means use your previous working, your previous answer. Hence deduce the coordinates of the points of intersection of the curve with the equation y is now f of 0.2x. So not f of x, but f of 0.2x. So the intersections with the curve and the coordinate axis. So that is the xy axis, right? So obviously, if we have a curve, right, like this, let's say, then where it crosses the x-axis is obviously the roots here and here, and the y-axis is the y-intercept here. That's what it's asking. Where would the points be in the x and y, where it crosses the x and y-axis with this new modified function here? So hopefully you recognise that this is going to be some sort of transformation of the original function, right? So before we get before we deal with f of 0.2x, let's just try and find the the intersections of just f of x, right? The function we have. So let's go down here. Okay, part D. So we have our function here, right? So firstly, let's look at the y, where it crosses the y-axis. So f of x, right? So it crosses the y-axis. When's that going to happen, right? When it crosses the right y-axis, that is when x is 0, right? So if x is 0, then y is going to be what? Well, if I essentially plug 0 for x here, it's just going to be minus 4 times minus 11. That would be positive 44, okay? And so that is my coordinate. So then that is the point x is 0, y is 44, right? So it crosses the y-axis at this point here. Then we can do the same to x. So it crosses the x-axis, and so that's when y is 0 now. Well, when y is 0, the function is 0. Then what we've got is that we have the brackets x minus 4 minus 2x squared add 7x minus 11 equals 0, right? I set the function equal to 0. So it's the roots essentially, right? So what we're gonna do is set each bracket to 0, each factor. So x is 4, or the quadratic equals 0. Now, so obviously we've got one solution, x is 4. But then we can deal with this quadratic. Now, what you'd realise is this quadratic, if you were to solve it, it doesn't have any real solutions. We can check that with the discriminant. So b squared minus 4ac for this quadratic here, well, b squared is 7 squared, then minus 4 lots of minus 2 of minus 11. If you put that in your calculator, you get minus 39, which is negative. So that means there are no real roots here. And so what that means is actually the only point we have where it crosses the x-axis is this x value here. So that will give the point x is 4, y 0. So in summary, we have the points f of x. The y-axis, it crosses the y-axis at the point 0, 44, and the x-axis at 4, 0, right? Those are my two, that's where it crosses each axis, that's what we just discovered. But that's for f of x, right? Now, the question said f of 0.2x. That's what the question actually says. Where would this new function, right, cross the same axis, the y and x axis, now? When now it's not f of x, but 0.2x. And the easy rule to kind of remember, the philosophy is, what we do inside the function, we do the opposite to what we expect. And obviously it affects the x values, because it's in my input of the function. So it affects x and it does the opposite. Well, what would we expect? What would this really be saying is this statement of 0.2x. Well, 0.2 times x, so you'd expect to times all the x values by 0.2. But instead, we're going to divide x by 0.2 instead. So divide x values by 0.2, right? So what that means is to obtain our new these points here, where it crosses the axis, to map that to this new function here. We're just simply going to do this little rule here. So firstly, 0.44, if we times x by 0.2, then 0 times 0.2 is still 0. So it's still 0 and 44. That is unchanged. So that is where it crosses the y-axis, the same point. But here, 40. Now, for 40, x is 4. So, what we're going to do here is divide by 0.5. So we're going to do divide by 0.2, sorry. Divide by 0.2 for 4, because x is 4. And remember, every x value needs to be divided by 0.2 here. So if we do 4 divided by 0.2, we get 20. So now the point is 20, 0. And that is the intersections with the x and y axis with the new curve there, okay? And so there we are. And so that's it. That's the end of the paper. I hope this has helped. But yeah.